Section 6.7 deals with the ideal and combined gas laws. So we've already looked at the basic gas laws and where they've come from, but then people wanted to combine them together and they wanted to make them more ideal. Now, me saying that gases are going to behave ideally is like saying life is going to behave ideally. It's just not true, but for the sake of this class and for the sake of simplicity, we're going to pretend that gases are well-behaved little atoms and that they are going to listen to every single one of those kinetic molecular theory laws that we looked at previously. So when we're doing it, that means that all of these atoms are going to follow these simple equations that you see here, where the top is the combined gas law because it combines Boyle's laws, Charles' law, and Guy-Lussac's laws. Here, this is the ideal gas law, where we can say, hey, if we've got some magic constant of R, maybe we can relate pressure and volume and moles and temperature all together in one pretty little equation. And then this last one is, hey, if we've got standard temperature and pressure, I know the volume of any 1 mole of any gas, and that is 22.4. So we get to use that like a conversion factor. So with this video, I want to break apart these new gas laws, that of the ideal gas law, and then also this 1 mole at STP. And we're going to look at those a little bit closer, and then we're going to do some practice problems that use the combined gas law or the ideal gas law. So, standard temperature and pressure, what are those values? Standard temperature just assumes 0 degrees Celsius, which is 273.15 Kelvin. Standard pressure is assumed to be 1 atmosphere, or 101.3 kilopascals. So just like when we're converting from grams to moles to molecules, etc., you can convert all of these units. So it just depends on how you want to express it. Physicists might express it one way, engineers another, chemists another. It just really depends. It's the same way as here in the United States, we report our temperature using the Fahrenheit scale, whereas in Europe, for instance, they might use Celsius. And so it's just a matter of looking at the units in it from a different vantage point. But all in all, this rule states that any 1 mole of any gas at standard temperature and pressure is always 22.4. So your problems might look something like, hey, you've got 2 moles. What's the volume? You could use the ideal gas law using each of these parameters where for temperature you plug in 273.15, for pressure you put in 1 atmosphere, or you could just note that if the gas is at STP, it's 22.4 liters per mole. So 2 moles would be 44.8 liters. All right, so within the ideal gas law, PV equals nRT, there's this new gas constant of the R. Now, for the most part in this unit, we're going to be using R as 0.0821 liters times atmosphere per mole K, and that's because these are the units that are most likely used in the gas constant. In the gas equations, the gas laws. Do notice that this is a K for Kelvin, and so you cannot use Celsius when you're putting your temperatures into this equation. You must use Kelvin. These other R values are important. It just depends on your vantage point and how you're using it. So for this unit, for gas laws, ignore all the other R's. Just focus in on this R, that R equals 0.0821. Now, your book has this table, table 6.1. I highly recommend printing it off and just letting it be there next to you. That way you have something to look at as you're doing these combined gas laws and gas law problems. With that, we have looked at all of them now, even if it's ever so slightly. So with the ideal gas laws, it's PV equals nRT. Combined gas laws, and then each of the individual gas laws. Avogadro's law we didn't really talk about much, but basically it's relating volume to moles. But they're all very similar, whereas if you combine them, you get this combined gas law. I've even seen moles included in the combined gas law, where N is down here with the temperature. So that being said, anytime you have a problem and it looks something like this, how you do these problems is very systematic. You identify your variables, which is what you can see here on the left hand side. So this problem says a scuba diver is initially at 1 atmosphere and submerges under the water to a new pressure of 3 atmospheres. Their lungs originally held 6 liters of water. If they held their breath as they submerged, which FYI is very bad, we talked about that earlier, what would be the size of their lungs at this new depth? So let's identify the variables, meaning we have one atmosphere. You have to decide, is that a pressure? Is that a volume? Is that a temperature? What is it? That's a pressure, and we know that because of its units being atmospheres. So this is your first pressure. 3 atmospheres is your second pressure. So I identify that as P1 and P2. And then they originally held 6 liters of air. So that's V1. It was original. Then what is the size of their lungs at this new depth? This tells me I'm going to be searching for a V2. So if we look back at this table and we ask ourselves, which of these equations have a pressure and a volume and nothing else? Everything else is held constant. I hope you zeroed in on this top one here, Boyle's law. Pressure times volume equals pressure times volume. And now it's just a matter of plugging in the variables into the equation. But if you don't first define the variables, you're going to be staring at that list of equations and having no idea which one to use. So I say identify the variables and then just use whichever equation makes sense. And it makes sense if it only has those variables and nothing else. Alright, so we plug in the values. 1 times 6 equals 3 times my new V2. Now in order to get the 3 to the other side, I need to divide, so this will look like 1 times 6 divided by 3 to give me a V2 of 2 liters. For our next problem, we're asked, if I have 75.9 moles of a gas held at a pressure of 5 atmospheres in a container with 50 liters, what is the temperature of the gas? I want you to stop the video right here and try and identify the variables. If you identify the variables, what you should have gotten is your moles, your N equals 75.9, your pressure, P, is 5 atmospheres, and your volume is 50 liters. And then it asks you for the temperature. So I always put T equals question mark. Now you might have started putting subscripts like N1, P1, V1. If when you get to the end and you only have 1s and you have no 2s, just erase all your 1s. It's okay. That kind of tells you that you probably are going to work with something like PV equals nRT, because this equation has everything we've got and nothing else except for that pesky R. So what do we do with the R? This is a new variable that was not defined in the problem, but you have to define based on your knowledge of this equation. And so your R equals 0.0821 liters times atmospheres per mole K. So now that you know all of these variables, you can plug them in and you can solve for your temperature. So by doing this, you'll take your N and your R, divide both sides by N and R, which makes it be PV divided by NR equals T. And then you plug that in your calculator, making sure you go 5 times 50 divided by 75.9, enter, divided by 0.0821. That's how I do it, just to make sure that you are using order of operations correctly. And you get a final temperature of 40 Kelvin. Notice I do have my units in Kelvin. Why is that? And that's because your R has units of Kelvin. Alright, if it doesn't ask you, change that temperature to Celsius or something like that, if it said that, you'd have to convert this back to Celsius. But if it doesn't say that, that answer is perfectly fine. Our next problem states a 550 milliliter sample of nitrogen gas is warmed from 77 degrees Celsius to 101 degrees Celsius. Find its new volume if the pressure remains constant. So stop the video and identify your variables. You should have had V1 equals 1 atmosphere, T1 equals 77 degrees Celsius, T2 is 101 degrees Celsius, and V2 is our unknown. So that being said, we know our equation that correlates each of these variables is V1 over T1. Now, this is where it gets a little tricky. You might be tempted now to just immediately plug in each of those variables into this equation. But that's not right at all. Now, why not? It's because your temperature always has to be introduced into the gas law equations in the form of Kelvin, not Celsius. So this is always wrong. You will always get the wrong answer. Remember, Kelvin equals degrees Celsius plus 273. So you can just take 77 plus 273 to give you 350, 101 plus 273 to give you 374. And now you can just plug those variables in and solve for V2. Now notice, in order to do this, I took 1 atmosphere divided by 350, hit enter, and then multiplied that by 374 to give me 1.1 atmospheres. Every one of these gas law problems is very similar, where they give you unknowns, they give you knowns, and they're asking you to first identify your variables, then figure out which equation to use, and then solve for the answer. So with this, we are finished with Chapter 6, which is all of the material for exam number 3. So go complete all of your homework and then take exam number 3.